My name is Roni Kabwe. I'm an advanced diploma student at University of South Africa, UNISA. And I'm going to be taking you through a presentation of a project that has been given to us by the lecturer, Mr. Ilonga. So, all right, without further ado, I would like to present my screen, obviously, and go offline. I prefer using Teams because I think it's more efficient than most of the program. All right, so I'll start by sharing my screen, obviously. Also, I will cancel my video recording. All right. Okay. There we go. As I was saying, my name is Roni Kabwe. I'm a professional engineering technician with EXA. And then today I'll be taking you, Mr. Ilonga, through my presentation of water infrastructure and resource management, which is WRM 3701. All right. Okay, so this is the overview of the presentation. We'll be discussing about the project brief, project data analysis and deliverables. We'll be touching into the design plan and result, where I will prefer to go through the Epanet file itself, and then I will conclude with the findings. So obviously, in our project brief in background. So we have our project, which consists of designing a water supply system in the TPC local municipality. This is actually a town layout of the local municipality, which is composed of 4 townships. We have Township 1, Township 2, Township 3, and Township 4. And then obviously in this area, you can see the Shikahilo Mountains. So I'd like to assume the geographical aspect of it as a quasi-mountainous area. So this stability studies of the entire hydraulic infrastructure, which is inclusive of pumping mains, back supply reservoir, and back supply mains in order to satisfy all the township that we are seeing in our screen. In the project data analysis and deliverables, we'll be dealing with the data that has been given to us. And as you can see, all this point that has been given to us as from the abstraction works, which is also the Nyangwa River. And then we'll be looking at the Shikaliho water treatment plant, and then the back storage reservoir. We'll be touching also at the Junction 1, Junction 3, and these 3 and 4 demand centers, 1 and 2 demand centers as well. These are the dimensions of the pipes or the length of the pipe that has been given to us. And obviously, we also have our heat use levels. And then we have been given as well the average daily demand in terms of liters per second, where we have Township 1 having 65 liters per second as the average daily demand. Township 2, average daily demand of 70. Township 3, average daily demand of 80. And Township 4, average daily demand of 140. All right. So the project deliverables that we focus more on is to actually get the water pump design. We're going to have also to deliver the back storage reservoir design, the pipe sizes. In terms of the pipe sizes, we're looking at the length of the pipes and diameters of the pipes. We'll be also delivering the flow rate and velocity design. Obviously, looking at the head loss and pressure result for each component in the water system. Full report means after you finish your design, there is this full report that we receive from Epanet file, which is giving, obviously the full result from 0 hour up to 72 hours, which is 3 days in our actually context. All right, so the Epanet design and analysis, which is the presentation, like I said at the beginning, I would prefer to literally open the Epanet file itself so that I can go through it step by step as what we have actually discussed. All right, so this is actually the Epanet file that we have, and in terms of the steps that's supposed to be followed. In step one consists of actually setting up the water supply network on Epanet. And as you can see, this is abstraction of works, which is our source that has been set. And then the pump, we have a pump to push water to the water treatment plant, which is also our reservoir 2. And we also have another pump, which is our second pump we are designed to push the water to the back storage reservoir. And you can see this one is quite a high one, 75 meters, and this one is actually sitting only at 12 meters. And then obviously we have the junction 1 going to junction 3, and then from junction 1 going to junction 2, and then that way they also distribute to obviously our demand centers. The inverted levels were calculated to find each elevation at each point. As you can see here at reservoir 1, we have the elevation which is sitting at 0 meters, which is our datum. And then we also have the water treatment plant, which is sitting at 12 meters. I will explain a little bit later down the presentation how we got to 12 meters. We also have our back storage reservoir, which is sitting at 74 meters, as you can see on the screen. And then we also have our junction 1 sitting at 47 meters, junction 3 sitting at 38 meters, junction 2 sitting at 40, the main center 1 sitting at 34 meters, the main center 2 sitting at 30 meters, the main center 3, which is sitting at 43 again, and the main center 4, which is sitting at 30 meters, all right? So the two pump, in terms of step 4, 2 pumps have been set up, which is the first pump here and the second pump. And then now, as you can see, the 12 meters, how did we get to 12 meters? Technically, when we have to do our workings, the reservoir 2 is sitting at 17 meters, 17 meters. But however, in the given data, they said that the outlet of the water treatment plant is sitting 5 meters below. So we did 17 minus 5 to find the 12 meters that we actually are showing in the screen. And obviously the storage reservoir is supposed to be set by the Shikaleo Hill, which is, you can see, it's actually sitting pretty high at the Shikaleo Hill. Sorry, this part 3, the Shikaleo, and then you can see the elevation is 74 meters. This is actually the highest point of the design, and it's pretty high. All right. So in step 6, it was asked from us to set the flow unit in LPS. So what we'll do is we'll go into options and then hydraulic. And then this is the LPS that was being asked from us. Obviously, from here, we're going to have to apply the Eisen-Williams equations. All right. And then we have to go to times and set our times. That was given in our data, which is 72 hours and 3 days technically, and then the pattern time step, which was set for 4 hours, all right? And then we also have our patterns, pattern that has been compiled by multipliers. These are the 6 multipliers that were given to us: 0.7, 1.3, 0.7 again, 1.3, 1.3, and 0.7 again. So this is actually like a frame that is, that we produce using these multipliers as of the average hour from 0 to 24 hours, all right? And then obviously we have also to go and check our curves and to see the flow and the head. So 620 liters per second was given to us, and then obviously we also have the head at 85. That produced this graph over here, all right? And then, which is okay. And then we have our storage tank, which is over this one. It's written that the storage required for tank is 10,244, which is over there. Use as minimum volume. Why are we using this as a minimum volume? Because we also have our workings that we have 12.5 meters high by 34.5 meters diameters. So once we calculate that, we are having 11,000 meters cubed. So obviously 10,244 is the minimum flow that we can receive in the tank, all right? So obviously now, if we run the Epanet, and then you can see our run was pretty successful. And then from here, the first thing that we did is we assume all these pipes to be 300 meters. And then after we assumed the pipe was 300 meters, and then we found out some of the negative pressures came back with a notification on the screen. So we had to readjust all these pipes throughout to find what is the required and the proper pipe to put, so that we cannot have negative pressures. So obviously that's how you can see in my screen. The final pipe that was found was 1,050 for pipe 1, 850 for pipe 2, 700 for pipe back storage up to the junction, and then 500 junction 1 to junction 3, 350 from junction 1 to junction 2, and obviously 220 for the main center 2, and 250 for the main center 1, and so on also on this other side. So So the trick here that we found is obviously the velocity cap is 1.5 meters per second. So we had to keep all the velocity below 1.5 meters per second. And even if I go to pressure and then I click on velocity and I run my simulation, you can see that all this velocity, this is pretty constant, but the rest of the velocity is actually below 1.5. So this is actually a good design. And I didn't only do that to keep the velocity below 1.5, but sometimes you'll find that the velocity to be 0.1, 0.2, 0.3. So what I did in that instance is I reduced the size of the diameter of the pipe to get the velocity a little bit higher, closer to 1.5 meters per second. All right, so this is the simulation that we run, and you can see already this is day 3 at 6 a.m. All right, so this program was pretty well very helpful for us to understand how the hydraulic system of the water supply works. It was very helpful, and it's actually helped the learner to understand how this works and to understand in terms of flow and velocity, and then obviously in terms of also adjusting the pipes and then the length of the pipes and the reservoir and how much water can be stocked here, obviously, and then given to the to all the demand centers. As per my simulation, so actually what I did is you can see at day 3, the storage is actually sitting at 14 meters. So that is in terms of water. So now what I did is put also a simulation whereby I close this pipe over here. So obviously this back storage tank will have to supply water in all the demand centers. And according to my simulation that I did, this back storage supply water for 29 hours, literally. So that will be also discussed in my conclusion. So this is actually the design that I made, and then you can see, and obviously the run is still successful. And in my conclusion that I will explain the part where I had to put valves around for pressure stabilization, all right? So I will just adjust this, and then we go back to Epanet. And then this is also the flow velocity diameters and total length and unit head loss. So this is the last diameters that we came with at the end of the design. The roughness was set at 60. Why? Because we're working with the HDPE pipe. So the coefficient of roughness of the HDPE pipe is 150 to 160. Now, obviously, we have our flow liters per second. We have our velocity. You can see all the velocity are below 1.5, and then the unit head loss as well, the friction factor, quality, which is 0, and the status of all the pipes should be open. All right, and then we also have our elevation, base demand pressure, and head. So this is actually showing our base demand in terms of the township, and then you can see these are the demand of the township that I also read at the beginning. Then we also have our head and our pressure as well. The pressure, it's always better for pressure to not exceed 90, but that's also obviously it's dependent from one municipality to another. All right, and then our last slide is actually speaking about the conclusion that we have found and achieved successfully as expected from a technologist in terms of the design water supply. So 2 pumps were actually put in the system, a back reservoir with calculated minimum capacity of approximately 10,244 meters cubes. And then obviously considering the sizes of the diameters tank that were given, will actually provide ample storage of the project water supply needed. Further analysis of the water supply, including head losses, hydraulic profiles, and pipe sizes have been conducted through the Epanet, like I was explaining in the Epanet file. Obviously, the back storage water provide water for the 21 hours without receiving water from the source when the pipe 2 is closed, explaining the simulation process. Obviously, the system satisfied the water demand with 2 additional valves. So I just put the valves for obviously pressure stabilization and to make sure that the system runs smoothly and the surge protection. And that was also simulated, and it also explained fully in the report. The summary result of all links, then all components are also enclosed. And obviously, all those, the last report that is enclosed as the annexure, it's explaining in terms of the flow rate that we have in each and every hour, the flow velocity, the pumping aid, and aid available from all the reservoirs. So this has actually been a good project that has assisted the learner to learn more about the hydraulic system and the water design. And then personally, I've learned a lot about this project, and it was very, very helpful to me as well as a learner. Thank you very much, Mr. Lunga, and I really hope that you find this very helpful. Thank you.